All right, hello. So here I'm just going to go over the 3 problems which I'm going to cover in recitation this week. So this is Monday, October 26th, I think week 11, dealing with sections 5.1 through 5.3, and then homework 10 and quiz 8. I think I got all those numbers right. So we're just going to do 3 problems where we use the eigenvalue method to solve a system of equations. So here we've got 2 variables, x1 and x2. And certainly you could use elimination to solve for both x1 and x2, but it's not as much fun as calculating some eigenvalues. So to do this, remember we want to set up this coefficient matrix here, where again this matrix A is defined by these coefficients. And the eigenvalues are going to be the zeros of the polynomial, which we calculate by finding the determinant, where I just subtract lambda off of each diagonal entry. And so easiest way to find a determinant for a 2 by 2 matrix is just to take the difference of the diagonal terms minus the off-diagonal terms. So diagonal, off diagonal. And then a little bit of algebra later. Lambda squared should be minus 6 lambda plus 2 lambda, so minus 4 lambda, minus 12 plus 7. And we get a nice polynomial in lambda, assuming I can do that. Yep. And so this will give us, if we factor, lambda minus 5, lambda plus 1. And so remember, we want the zeros of this polynomial. Those are our eigenvalues. And so lambda 1 is going to equal 5. Lambda 2 is going to equal negative 1. All right. So I'm going to, for now, let v1 and v2 be the 2 eigenvectors associated with lambda 1 and lambda 2, respectively. And so remember, now that we've found these eigenvalues, a general form for our solution will look like the following. Remember, v1 and v2 are both vectors of length 2, where if you read across the first row, you'd have the solution for x1, and if you read across the second row, you'd have the solution for x2. So actually all we have left, sort of using this method, is to find the eigenvectors v1 and v2. So there are a bunch of different ways to do this. I'll just go with the way your book does it. So if you'll recall, any vector, and we'll say v1 maybe is equal to ab. If v1 is an eigenvector associated with eigenvalue 5, remember that means that v1 is a vector that satisfies the following equation. And so what this is basically saying is that when I multiply this vector AB times this matrix, I could have alternatively just multiplied each entry by 5. So if we actually set up this system of equations, this gets us the following 2 equations. 6a minus 7b is equal to 5a, and a minus 2b is equal to 5b. All right, so there's actually something a little quicker we can do, because notice here, this is immediately going to translate into, a minus 7b is equal to 0 and a minus 7b is equal to 0. So we're going to see that we get sort of a set of two redundant equations, which is very good, which should always happen when we're doing eigenvalue calculations like this. If you want to sort of skip one of these steps, you could alternatively note I could have also just, and this is, I'll write this out sort of in general for any eigenvalue, but I'll use lambda 1 for now. Notice I could have alternatively just subtracted this eigenvalue lambda 1 from the diagonal and set up the equation like this. And basically all I'm doing is I'm sort of doing this step where I subtracted the 5a and 5b over to the left, but just one step earlier. So sort of the way I generally think about this is I take my eigenvalue, I subtract it off of each of the diagonal entries, and then I solve this associated system of equations. And so notice here, we get a minus 7b, a minus 7b. So because these are redundant, notice basically they're the same, well, they're the exact same equation, not even basically the same. There's actually going to be infinitely many choices for a and b which satisfy this, right? I could pick anything for b, and then I just have to pick the right number for a that's going to make sure that that equation zeroes out. And so I'll probably just let b equal 1, a equals 7, and that'll give me a solution. And so v1, my eigenvector, you get should be 7, 1. All right. Now, in order to just save time and so we can get to the others, I'll say the eigenvector I got for lambda 2 equals negative 1 was 1, 1. I can give you a little bit of a trick here that I like to use, or I guess that everyone uses at some point, but I certainly didn't invent this trick. Notice that if you add across the rows in this matrix A, they all add to the same number. So notice here, 6 minus 7 is negative 1, 1 minus 2 is negative 1. And whenever you get that property that all of the rows add up to the same value, 1, 1 is always going to be an eigenvector. Because if you notice, basically 1, 1 is just asking you to sum each row individually, and that gives you the values of a times v2. So here are our two eigenvectors using the general form for a solution. We get the following solution. As a general solution. And remember, this vector here is just the vector x1, x2. So this is actually giving us, in a way, two equations, one for x1, one for x2. But this is kind of just a more compact way of writing it. All right, so what I want to do next is go over a 3x3 case. So we should wind up with 3 equations for 3 variables. All right, so for the next problem, we're going to look at a system with 3 variables and 3 equations. And so using the eigenvalue method, this will be basically the same actually as when we did the first problem, just a little more involved because we've got 3 variables. So to find a solution to this, first thing we're going to do is we're going to set up the associated matrix A and calculate its eigenvalues. So there are a couple tricks you might notice right off the bat. So because A has 2 identical rows, we know one of the eigenvalues has to be 0. On top of that, again, if you look at the sums of all of the rows sum to 9. So we know an eigenvalue has to be 9 with eigenvector 1, 1, 1. That being said, I'm still going to sort of lay out the general process for how you'd set this up to find the eigenvalues if maybe you didn't have sort of nice properties like that to kind of let you guess. So again, what we're going to do is we're going to calculate the determinant where I've subtracted off lambda from each diagonal entry. So there are many ways to calculate a 3x3 determinant. I'm going to do it the way that I tend to prefer, which is cofactor expansion. So I'm just going to basically expand across this first row, although you can do this with any row or any column, sort of in the same process. And what you do is you take one of your elements, cover up its corresponding row and column, and then multiply by the determinant of the 2x2 matrix of what remains. And so you can do this again, like I said, with any row or column, because you can just pick a row or a column and do this same process where you sort of work your way down the row or column, cover up the row and the column of that particular element, and then sort of just keep calculating those determinants. However, as we cycle through, we want to make sure to plus, minus, so the signs should change of each of these terms. So now 1, I'm going to cover up the middle row, top column, and I'm left with the determinant of 1, 4, 1, 4 minus lambda. And then finally 4, I cover up row 1, column 3, and I'm left with this determinant. And we go plus, minus, so now I'll add 4 times the determinant 1, 7 minus lambda, 4, 1. And so now this is I guess a combination of 3 determinants, which are a little easier to calculate because we can just take the cross products, or we can do this sort of in the standard way to calculate 2x2 determinants. And sort of unfortunately, we do wind up with a kind of annoying polynomial that we have to work through. But it's just algebra, so it's not too scary. All right, we got all that. And since algebra is so much fun, and I don't want to deprive you of being able to work through this, I'll tell you that multiplying everything through, combining like terms, and working through it all, you should get the following polynomial as our characteristic polynomial of this matrix A. Minus 54 lambda. All right, so we want to factor this. Factoring 3x3 polynomials can be tricky. Again, sometimes we might need to guess a root right off the bat. Here, it's actually, we've got one trick. Since there's no constant term, we can factor out a lambda. And because I prefer to look at degree 2 polynomials where the leading coefficient is positive, I'm actually going to factor out a negative lambda. So notice I just factored out a negative lambda and changed the sign of each term here. And so now notice this factors to give me negative lambda times lambda minus 6 times lambda minus 9. All right, so that gives us 3 eigenvalues for this matrix. Equals 9. So, like I said, we could have guessed 0 and 9 right off the bat. Again, 0 because 2 rows are the exact same, and 9 because the sum of all of the rows is the same. 6, I think, might have been a little harder to guess. So I think it was still worth sort of working through this whole process. All right, so next step in this process of solving the system of equations, we need to find eigenvectors for each of these three eigenvalues that give us a general solution. So I'll sort of give you a few tricks maybe you can use, but like I said, for at least lambda 2 equals 6, I think it's a little less obvious to kind of guess. But so for lambda 1 equals 0, notice that if I look at columns 1 and 3 of this matrix, they share identical entries all the way through. So if I ever see two columns like that in a matrix, I can always just sort of alternate 1 and -1 in my vector. And then A times V1, notice, (0, -1). When I do this multiplication, the 4 and 4 are going to cancel out, the 1 and 1 are going to cancel out, the 4 and 4 are going to cancel out. And so sure enough, this is an eigenvector with eigenvalue 0. Now for lambda 3 equals 9, since all of the rows sum to the same value of 9, I can just use the vector 1, 1, 1. And again, this holds 2 by 2, 3 by 3, 4 by 4. Any matrix where the row sums are all the same, you can just always do this. All right. Lambda 2 equals 6. I think we're going to have to do it the little more involved way. So remember what we want to do. We want to solve the matrix equation where I subtract lambda off of each of the diagonal entries of A and solve for the eigenvector V. So this would look like this. And we'll say my eigenvector B will be represented by ABC. And this is equal to 0, 0, 0. So this is what the matrix equation looks like. Maybe a slightly nicer way of looking at it, -2a plus b plus 4c is equal to 0. A plus b plus c is equal to 0. 4a plus b minus 2c is equal to 0. So we get 3 equations and 3 variables, so certainly we can solve for a, b, and c. Maybe what I'll do, just to make this arithmetic a little easier, is I'll number these 1, 2, and 3. So starting from top to bottom, 1, 2, 3. And we'll just start combining these and see what happens. So if I do 2 times 1 plus 3, that cancels out the a's, and I get 3b plus 6c is equal to 0. All right, and so from here, since I know that 3b plus 6c is equal to 0, remember, I know that if 6 actually is an eigenvalue of this matrix, then these 3 equations should be somewhat redundant. That means that basically these equations aren't independent of each other, that I should be able to combine 2 of them and get the other. Another way of thinking about this is that one of these variables is in a sense a free variable. So given that fact, one trick I can kind of do is, well, okay, I know that b and c have to satisfy this relation. So maybe to save on a little bit of time, what I'll do is I'll kind of just make a guess that since b and c have to satisfy this equality, maybe if I let c equal 1 and b equal -2, I can plug those into the other three equations and figure out what value a has to be given these two choices for b and c. So from equation 1, if I plug in -2 plus 4, that would be -2a plus 2 equals 0. Equation 2, I would get a minus 2 plus 1, so -1 equals 0. Equation 3, I would get 4a minus 2 minus 2 minus 4 equals 0. So notice the same value of a satisfies each of these three equations. A equals 1. And so an eigenvector for lambda 2 equals 6 would be the vector 1, -2, 1. So what I did here, I sort of started with these equations, combined a few to eliminate one of the variables, made what I felt was a reasonable guess for the values of b and c, and then made sure that, okay, if these are the values I pick for b and c, will this work with the rest of the three equations, right? What you want to make sure is that a, in order to satisfy all three of those equations, should take on the same value. Of course, you could solve this by working with these three equations a little more and sort of crunching things down a little more than that, but this is sort of a nice way to save time. All right, so given these three eigenvalue, eigenvector pairs, we get that a general solution of this system of equations is equal to constant 1, 1, 0, -1, plus c2 e to the 9t, 1, 1, 1, plus c3 e to the 6t, 1, -2, 1. Additionally, if you wanted to list all of these out by their individual variables, you could do that. So this would be c1 plus c2 e to the 9t plus c3 e to the 6t. And again, you're just reading across, so this would be 0 times c1, which is 0, plus c2 e to the 9t, minus 2c3 e to the 6t, and then negative c1 plus c2 e to the 9t plus c3 e to the 6t. And so if you prefer to list each of these out based on their variable, again, x1 corresponds to first row, x2 to second row, x3 to third row. All right, and the last problem I wanted to go over, like I said, is another case with two variables, but it's going to have complex eigenvalues, as we'll see here in a second. So using the eigenvalue method, we're going to calculate the determinant, or again, I'm subtracting lambda off of each diagonal entry. And if you work through this, you should get that this has a characteristic polynomial, lambda squared plus 4. And so that would give us two zeros to this polynomial, plus or minus 2i. So this isn't a coincidence. It turns out that eigenvalues always come in conjugate pairs. And actually it turns out that, so if we think of these as two separate eigenvalues, their eigenvectors actually also come in conjugate pairs. So that is, if v1 is an eigenvector of lambda 1, then the eigenvector, or a eigenvector, I guess I should say, of lambda 2 is just the conjugate of v1. So kind of good thing to keep a note here. For this, actually, we'll only need one of these two eigenvalues. So we'll work with 2i. And one of these eigenvectors, v1, and we'll be able to calculate the remainder of the solution actually just with these two things. So given lambda 1, if we want to find v1, remember we want to solve the following matrix equation. Where here this vector AB is our vector v1, and that's all equal to 0. And so multiplying this out, we get the following two equations. So these two equations should be redundant, although it's a little harder to see when we've got complex eigenvalues. However, remember, because they should be redundant, we only really need to work with this first equation to, I guess in a sense, kind of find the eigenvector, AB. And notice, we just need to make sure this first equation is equal to 0. So I'm just going to let v1, I'll let a be 5 and b be 1 minus 2i. And this definitely is a solution to this equation. We should quickly double check that it's a solution to this equation. Make sure that this is true. Well, if we expand this part out, we get -1. Notice the middle terms, so -1 times -2i, +1 times -2i cancel. So we're just left with minus 2i squared, which is equal to 4 times I squared, which is -4. And so notice this product actually does work out to -5, so we're all good there. So this is a valid eigenvector for the eigenvalue +2i. All right. So given this, we know that a general solution will look like the following. E to the 2i times t. And so expanding this out using Euler's formula, we get the following. And so now we can actually distribute this through to this vector to calculate that x of t is equal to the following vector. So this is after a little bit of simplifying. So we only need to find one eigenvector here, because this vector will actually correspond to two linearly independent solution vectors, x1 and x2, defined by the real and imaginary parts of x. So the real part here is just the vector corresponding to all of the real valued entries, or real valued coefficients, I guess I should say. 2t and cosine 2t plus 2 sine 2t. So notice it's all of the basically terms not containing I. And then a second linearly independent vector can be found by looking at the imaginary coefficients of x. And this will just be all of the coefficients attached to the i's. Both of these will be real vectors, though. As again, we're only looking for the coefficients. So coefficients attached to i's. So using these two vectors, then, a general solution to this system of equations will have the following form. Where again here, x1 is the real part, x2 is the imaginary part. And so, again, complex eigenvalues really aren't, they're a little scary, I think, because complex numbers are always a little weird, but I think they're kind of nice. You only have to find, one eigenvalue, eigenvector, and we get a nice general solution. So that wraps up basically what I wanted to go over for this week. As always, feel free to email me, contact me if you have any questions. Yeah.